We're going to look at the very basics of what's known as hypothesis testing in statistics. So the background before we jump into it is that a hypothesis is a claim or a statement about a property of a population. These can come in all sorts of different varieties. Now the hypothesis test, that is the procedure that we're going to use for testing the claim that's being made about that property. So for example, let's say that you have an article that claims that 45% of individuals prefer brand A to brand B. Well, let's say that we take a sample and we find that in our sample 48% prefer brand A to brand B. What a hypothesis test is going to let us do is it's going to let us determine, is that 3% difference between our two values here, is it significant enough to say that, you know what, the 45% is probably not an accurate value? So that's what a hypothesis test is going to allow us to do. Now we're going to run through the basic steps of determining or of doing a hypothesis test. And the first thing that you would need to do is you would need to determine the type of test that you are working with. So the basic options that you'll see in most introductory statistics level are going to be working with proportions, working with means, or working with standard deviations or variances. Now, an example of each of these. So a proportion, maybe you see something that says 40% of people say they go out to eat one time a week. Okay, that would be a proportion because it's telling us what proportion of the population do a particular thing. It doesn't always have to be in the form of a percent. It might have instead said that 20 out of 50 people said that they eat out one time a week. For a mean hypothesis test, we might see something where we hear that the mean wait time at a particular doctor's office is a certain amount. And then for the standard deviation or the variances, maybe we are interested in looking at the standard deviations of test scores for different college classes or something like that. Okay, now the second step. So once you've decided what type of test you're going to do, the second step you need to do is determine what's known as our null and our alternative hypothesis. The null hypothesis, which oftentimes we will use the notation H sub 0, that comes from the original claim. It does not come from the sample that you are going to take. Okay, and it is a statement that the value of the population parameter is equal to some claimed value. Now, when we're doing this hypothesis test, we are actually going to we're trying to prove that the null hypothesis is false. That's usually going to be our goal for a hypothesis test. Now, this seems a little bit strange to people sometimes, but I will give you an example in just a second to try to illustrate why we try to prove that the null hypothesis is false. So the null hypothesis is our original claim, and that the value is equal to some claimed amount. Now, the alternative hypothesis, this is usually actually what we are interested in, and it's going to be a statement that the parameter from our null hypothesis is different than what is claimed. So we are typically going to see either a less than symbol, a greater than symbol, or a not equal to symbol in our alternative hypothesis. Now, to decide which of these symbols you would use, you would have to understand what is the goal of the study. So if we look at the mean wait time at a doctor's office, maybe we're interested in finding, is the mean wait time lower than what was claimed? Well, if that's the case, then we would use the less than symbol because we were because it indicated we're looking at it being less than, we're looking at it being lower. If we were interested in finding out if the wait time was longer than what was claimed, we would use the greater than symbol. If we're just interested in finding if whether it's different from what was claimed, then we would use the not equal sign. So the symbol for your alternative hypothesis will be determined by the goal of the study or what you're trying to show. Now, as I mentioned earlier, I said with a hypothesis test, we are usually trying to prove this to be false, because that would in turn then allow us to show that whatever we have for our alternative hypothesis to be true. And still some people wonder, well, why don't we just try to prove that the alternative is true as opposed to trying to show the null is false? And the example I'm going to use is, let's say that for our null hypothesis, we say that all dogs have 4 legs. Okay, so let's say this is our null hypothesis. This would be equal, so the number of legs equals 4 is what our claim is, so we have that equal to quantity. So if I consider this null hypothesis, this is actually very hard to prove that it is true, because let's say I take a sample of 10 dogs and all 10 of them have 4 legs. That does not prove that all dogs have 4 legs. But if I try to show that this is false, all I would need to do is to find one example of a dog that didn't have 4 legs. So maybe I have a dog that has 3 legs. So that one example is enough for me to prove that this is false, and then by default, my alternative hypothesis would need to be the true statement. So that is why when we're doing hypothesis testing, the alternative hypothesis is usually what we are interested in. It's what we are trying to show to be true. But we show that this is true by proving that the null hypothesis is actually false. Okay, once we get our null and the alternative hypothesis done, then we have to determine what our significance level is going to be. And that's represented by the Greek letter alpha here. Now, our significance level is the probability used as the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. Now, for your typical statistics problem, they will tell you the significance level. The most common ones are 0.05 and 0.01. If you're doing your own research, you can technically pick whatever significance level that you want. Now, with significance level, though, because it's a probability that allows us to determine whether we have significant evidence or not, there is the potential of getting an incorrect answer, an incorrect result. So we have what's known as a type 1 error. So in that situation, that is when we go through the hypothesis test and it tells us to reject the null hypothesis. So it's saying the null hypothesis is false, but in real life, the null hypothesis was actually true. Now, we typically don't know if we make these types of errors because it's not an error that we did by computing something wrong. It comes down to maybe we just got an unlucky sample that showed a trend that really doesn't exist. The probability of making a type 1 error is equivalent to our significance level, alpha. Now, the opposite of this can also happen. We can have what's known as a type 2 error. This is when our hypothesis test tells us that we should not reject the null hypothesis when it actually is false. And again, we aren't going to know if we make this error because it would come down to we maybe just got one of those samples that didn't show what was actually happening for the entire population. The probability of a type 2 error is known as beta, and we aren't going to worry about doing that calculation at this particular point. Okay, the fourth step. Now we're actually going to have to compute what's known as the test statistic. This comes from your sample, or your sample of data, whatever you gathered. So our test statistic is not from the original claim that we read or that we hear. We compute the test statistic from your sample that you take. Since we're just doing the basics of hypothesis testing right now, we aren't actually going to look at the different formulas we use because each type of hypothesis test has a specific formula used to calculate the test statistic. So when we go over each of the different hypothesis tests individually, that's when we will look at those formulas. Okay, now step 5. Here's where we have a little bit of divergence. We have two primary methods that we use for hypothesis testing. We have one method that's called the p-value method, and we have another one that's called the critical value method. No matter which of those two methods we use for step 5, once we do whichever method we pick, then we are ready to make our decision about the null hypothesis. Now, for both of these methods, we must know if we have what's called a right-tailed, left-tailed, or two-tailed test. And this is going to come from the alternative hypothesis. So, if our alternative hypothesis has a less than symbol in it, what we would end up having is a distribution like this. And since we're interested in whether our sample was less than whatever the claimed value was, we are looking at the left side over here. So this right here, this would be considered a left-tailed test. Okay. And this region down here, that's what's known as our critical region or our rejection region. And the area in this portion here is exactly our alpha value. So it is exactly equal to whatever our significance value is. Now, if our alternative hypothesis has a greater than symbol, so whatever we're trying to figure out, if our alternative, we're interested in it being larger than the claimed value, well, on our distribution, we would be looking at values that are higher up here. So our area up here, again, would be equal to alpha, and this would be considered a right-tailed test. Because, again, our critical region or our rejection region here is on the right side of our distribution. If our alternative hypothesis has a not equal to symbol in it, so all we're interested in is finding whether or not our sample is showing that it's not equal to whatever the claimed value is in the null, then we have what's known as a two-tailed test. Because we could be lower than the claimed value, or we could be higher than the claimed value. We're not specifying which direction we are interested in. So this would be considered a two-tailed test. Now, with a two-tailed test, we actually have to do a slight modification to our alpha, because alpha represents the total area of our critical regions or our rejection regions here. So because we have a two-tailed test, we have to split that alpha between the tails. So we would actually have alpha divided by 2 as our area in each component of our hypothesis, or in each component of our rejection region. So the total area here would be equal to alpha, but if we were to just look at one section individually, that would be our alpha divided by 2.